as I will show you that through some Bayesian inference and some toy galaxy modeling, we can reconstruct this 3D configuration pretty accurately and reproduce all the observables, including surface brightness, the 2D axis ratio, as well as the images. So why do we need deep projection? Primarily, I think, because the 2D observables are usually misleading, including the sizes that we measured and the axis ratios that we measured. For example, here I show you with 1,000 toy galaxies. I will talk to you later what we mean by toy galaxies. But here, let's focus on the plot. Here I show you the 2D semi-major axis effective radius as you would measure from Gauss-Fit versus the 3D spherical half-mass radius as what typically people measure in the simulations. Okay? So you can see that depending on the intrinsic shape, which is the color here, and depending on the line of sight, which is not shown here, the 2D shape and 3D shape can differ by up to a factor of 2 in either directions. And this is simply due to a projection effect. Throughout this whole talk, I will not touch the topic of mass-to-light ratio gradient. I'm talking about a purely geometric effect. Okay. Another way to look at this is on the same space, but we here color code the galaxies by the Sausage index. You see a systematic trend with Sausage. So even for oblate and spherical systems, there is a difference between the 2D and 3D shapes. Okay. Not only the sizes. Not only the sizes are different, but also the shapes. But before moving on to the shape differences, let me give you some practical things that observers can use. So here is a plot based on 50,000 toy galaxies. I'm showing you the Sausage index versus the apparent 2D shape. Okay, so the color is the average, the 3D half-mass radius in units of 2D semi-major axis effective radius. And you can see this trend with Sausage index and with 2D shape, and this empirical correction corresponds to the red contours. So you can, on average, map 2D size to 3D using an axis ratio in units of 0.5 to a power of 0.3 times an exponent, which is a function of Sausage index in units of 2.5. This correction formula is more accurate than any empirical corrections that is currently used in the literature. But again, this is all on the average sense. For individual galaxies, 2D size and 3D size can differ dramatically. So shapes can also differ dramatically. Okay? So this is the 3D shape P versus the 3D shape Q. So P is the ratio between the minor to intermediate axis, and Q is the ratio between the intermediate and major axis. The color is the observed 2D shape, so capital Q, capital B over A. So you can see that for the same kind of galaxies, for example, prolate systems here and oblate systems here, you have a wide range of colors, similarly wide range of colors. On average, right, for prolate systems, the average axis ratio is 0.4, but the same axis ratio values can easily be achieved by oblate systems here if you look at this variance map. Okay. So more specific motivations for deep projection. So we learned from multiple simulations that galaxies are more prolate at higher redshifts or when they are dark matter dominated or they're below some critical mass. So Avishai Dago will talk more on this topic on Thursday. But today, let's see, do we have observational evidence for this? I think we do have preliminary evidence from the candle survey. So this is the work by Jiang et al. And this is showing you the 2D axis ratio versus the 2D size. And so from the left to right, you have increasing mass, and from the bottom to the top, you have increasing time. So you can see that at late times and in the massive galaxies, they tend to populate this upper right corner, which is where oblate disky systems would be. And at early times and below this critical mass, which is around the stellar mass of 10 to the 10-ish, galaxies tend to populate the bottom left corner, which is where prolate systems would be. But this is in a statistical sense. Can we test this scenario for individual galaxies in large redshift surveys? Okay. Also important, we have this business of low surface brightness galaxies or ultra diffuse galaxies that people will talk about on Wednesday, I think. I think shape measurements, the intrinsic shape measurements can help us to distinguish the two competing formation scenarios. So one scenario is that bursty star formation leads to repeated supernovae outflows which puff up dwarf galaxies. And this is seen in the Nihao simulations and also in the FIRE simulations. A competing scenario is that the UDGs or low surface brightness galaxies in general populate the high halo spin tail, so they are oblate disky systems. So for example, here we measure the shape of Nihao galaxies. So this is flattening, this is elongation, and the UDGs are highlighted in red. You can see that UDGs are, on average, prolate or triaxial systems. So this is in line with the first scenario. A better way to see this is on the right-hand panel. So here we measure what we define as a contrast parameter. This is a contrast of star formation rate fluctuations. We measure it over time windows of duration tau. Okay. So you can see on this parameter space, the UDGs or low surface brightness ones clearly stand out as the higher burstiness systems. And from the low burstiness to high burstiness, you can also see this color gradient, which represents shape distribution. You go from exclusively oblate systems when you are less bursty to a prevalence of prolate systems when you have high burstiness. Okay. So these are basically our motivations for doing the deep projection for individual galaxies. And I mean, doing the deep projection for UDGs is very practical because all the observations are very, very deep. Even for the small telescopes like a Dragonfly, with several days observation, it can reach surface brightness as low as 30 magnitude per arcsine square. So is it possible at all? That's the key question. We know that it's a classic problem and it's very hard. It took generations of astronomers to figure it out. I think the consensus today is that the deep projection is usually not unique. As these people have contributed. And there is the concept of the Conus density, which basically says you can always vary the 3D density here and there at some particular locations to some extent without changing the 2D surface density distribution. So the extent of Conus density is minimized only when you are perfectly edge-on and when you are perfectly oblate. You can circumvent this Conus density by introducing, by assuming some density profile for the galaxies. And even more, nowadays we have deep surveys that can probe the low surface brightness component out to several effective radii. For example, here is the hypersupreme camera data of early type galaxies. You can see the surface brightness distribution extend out to almost 100 kiloparsecs. So our hope is that maybe we can use this high quality imaging to break the degeneracy in deep projection. And of course, here I'm here to give you hope. So I will show you with a proof of concept test on our toy galaxies that this is feasible. Let me walk you through a few examples before I wrap up with the methodology. Okay. So here is the same galaxy that I showed you in the beginning. It's a prolate system viewed from very close to head-on. So here we have the observables like surface density, axis ratio profiles, and we have this mock image. So the red represents the true intrinsic configuration. So the red vector is the true line of sight. And through some basic inference, we can reconstruct the image as well as the surface density profiles. And here on the lower left panels, we show you the posterior distributions of the model parameters, including the shape, PQ, and the line of sight, which is specified by an azimuthal angle phi and the polar angle theta. So the true values are represented in red, and the different shades of teal represents the posterior. So this is very accurate. Another example is an oblate system viewed from face-on. Here you have accurate reconstruction for most of the parameters except for this azimuthal angle, which you can kind of expect because we have some degree of freedom along the minor axis. Similar example of the same nature. we have another example of all oblet systems viewed from intermediate line of sight. We can get most of the parameters acceptably accurate. Here is the oblet system's edge on. The principal shape axis Q is significantly off, but the other parameters, including line of sight, are quite okay. So I wouldn't bore you with all the examples. Here is an intermediate example. It's a triaxial system viewed from intermediate line of sight. So this is the more general case. And I would say the result is pretty acceptable, except for some degeneracy stripes. And the last example is where we see multiple modes in the posterior distribution. So the lesson learned from this example is that it's not always good to use the median of the posterior distribution, but instead we can play with the combination of the modes in different parameter spaces. So to summarize what we learned from this toy modeling, we see that oblet systems, depending on whether it's face-on or edge-on, we have constraining power on most of the parameters, but not on the line of sight or one of the shape parameters. For prolate and triaxial systems, the results are usually acceptable. And sometimes we need to use mode instead of the medians. So before wrapping up, let me show you very briefly our methodology. So this inference process involves a toy galaxy generator. It's a Monte Carlo toy galaxy generator, and also the Bayesian inference tool, which is the publicly available version of the Dynasty. It's a dynamic nested sampling tool. So what we mean by galaxy is toy galaxy is the following. We assume galaxies are a collection of coaxial ellipsoids with constant axis ratios in 3D from inside to outside. And we assume the stellar particles follow Inastel profile. Note that Inastel profile is typically used to describe halos. But if you look at the functional form, it's actually almost identical to the Sausage profile. And we have tested that when projected, Inastel profiles produce 2D profiles that are very similar to Sausage profiles. Okay. So we populate stars according to Inastel, and we stretch the system to achieve the desired axis ratios in 3D, and finally we project. So in total, we have 6 free parameters, 2 for densities, and 2 for shape, and 2 for line of sight for a galaxy of a given mass. And in practice, we use the following Bayesian inference procedures. We break the process into 2 steps. First, we use the 1D profiles, the surface density and the axis ratio, to put constraint on the density profile parameters. So we try to use the surface density and axis ratio on equal footing by playing with the weights here. We assume uniform priors. And for the second step, we use the full image. But here, we only allow 4 parameters to be free. We fix the density profile parameters to the results from the first step. And this is all found by trial and error. And we play with different ways to achieve the best accuracy and the least degeneracy. And we use the Dynasty algorithm instead of the popular MC algorithm, MC. So that one is unfortunately devised for unimodal posterior distributions. And to summarize, the inference procedure is pretty reliable. We can always get a good correlation between the inferred parameter versus the true parameter. So here I show you the density profile ones and the shape parameters, as well as the line of sight angles. So to summarize, I think it's hopeful to infer the 3D structure and the shape just from 2D imaging, depending on a couple of reasonable assumptions. And I have showed you if you don't do this, and if you rely on 2D measurements to say things about galaxy shape distributions, you can be very wrong. And a correction formula from going from 2D size to 3D size is given here. Thank you for your attention.
Okay, questions for Fangzhou? Students first. Any students? No? Frank?
So, regarding Conus densities, right? As you know, the Conus densities basically are mathematical script to describe how you, at some points, add density and at some points subtract density. And it makes the density profile less smooth.
Yeah.
What you've shown is that if you make a model that is smooth inherently,
Yeah.
and you make same model in your inference.
Exactly.
You can recover that.
Yeah.
But if you take a disk bulge system, which has a non-monotonicity
Yeah,
and the derivatives, I can imagine that that really starts to screw things up. So the question
Yeah.
is, have you tested that? And the other question is, we never have access to the real projected density solution, but to a seeing convolved one. And seeing convolution would also wreak havoc on this. So have you tested those two issues?
So for the first, I think, of course, this inference procedure has limitations. As I put in the title, this only applies for like a smooth component, optically thin galaxies. So for a bulge disk system, you have to do like two of these toy galaxy components. So you essentially introduce many, many more parameters. So this would, I can imagine this can screw things up, but we haven't tested this. But we have tested is to use a bunch of simulated galaxies to test this version of simple toy galaxy. And I think the assumptions are pretty accurate for at least low surface brightness galaxies, notably UDGs and LSBs. And your second, yes?
Seeing convolution.
The seeing convolution. So we are trying to add noise and also convolve the images with a blurring kernel in the center, but we have not put it into like a production mode yet. Thanks for the tips.
Okay, so the next speaker, Arhen, who can come and maybe set up. And while we wait for Arhen to set up, maybe we can take another question. Maybe one question from me. Have you looked at the morphology of like of UDG in how it depends on the environment, like isolate UDG versus cluster UDGs? Do you see any differences in the?
So this is actually the thesis of our earlier paper this year with Avishai and Jonathan. So we use the Nihao and another galaxy group simulation to study UDGs in the field and in a dense environment separately. And we think the upshot is for a typical dense environment like the coma cluster environment, where you find both red UDGs and maybe on the outskirts blue UDGs, the contribution from this bursty star formation and also from the tidal puffing up is comparable. Yeah, that's the upshot. Yeah.
Interesting. Thank you very much. Yeah. So let's thank the Fangzhou again.